Welcome back to the YouTube channel, ladies and men. Today we are going to talk about the two's complement. It's the continuation where we are going to convert from two's complement form to the decimal equivalent. And then we are going to do some addition of decimal numbers by using two's complement form. So how are we going to do this? Well, first of all, let's do some examples on how we can convert from two's complement to decimal. So this is how it's going to work. Let's say we have, we are going to focus on 8 bits, obviously, in this video also. If you have any doubts regarding that, please let me know in the comments so that I can help you with that. So let's say we have 1 0 1 1 0 1 1 0. Okay, so there are 8 bits. So this is the two's complement form of a decimal number. Now we are going to decode this. Okay, so the first thing you have to look for is the first bit. Okay, if the first bit is 1, that represents a negative number. Okay, if the first bit is 0, that represents a positive number. I'll attach the introduction video in the link in the description, so you don't have to worry about that. You can go watch and come. If you had already watched, you know what I mean by this. Okay, so since this one is 1, we can say this is a negative number. If it's a negative number, you have to do the same thing. Okay, you have to do the same thing you did when you were finding the negative form of a positive number. What did we do? First of all, we converted to the ones complement. So we'll do the same thing. So the ones complement of this number will be 0, 1, 0, 0, 1, 0, 0, 1. Okay, so this is the ones complement of this number. Okay, now what you have to do this, we have to add 1. That's all. You have to do the same steps again and you will get the decoded value. So what will be the addition of 1? Well, that will be 0, 1, 0, 0, 1, 0, 1, 0. This will be the two's complement form. So this is the two's complement representation. Okay, two's complement representation. If this is x, this is actually negative x. Okay, if this is x, this is negative x. So we know this value is equals to, well, this is 64 and this is 16, 8. So 32, 16, 8. So 72, 72 and 2, 74. So this number is equals to 74 to the base 10. Well, we know this number we don't take into consideration because it represents the sign, and these 7 bits only represents the magnitude of the decimal, and we are just converting the binary to decimal here. That's straightforward. Okay, so this is 74 to the base 10. So minus x is equals to 74 to the base 10. Well, then x will be equals to negative 74 to the base 10. Okay, so this is how you have to decode a two's complement form number to the decimal number. Okay, so this is for negative numbers. If it's a positive number like this 0 1 0 1 0 0 1 1, well, what will you do? Since the first digit is 0, okay, the most significant bit here is 0. This is a positive number. Okay, this is a positive number. So you can directly come up with the answer. So 64, 80, 83. So it will be equals to 83 to the base 10. You can directly come up with the answer. Okay, but on the other hand, let's say you had a number like 10, 10, 11, 01. Well, in this case, the first number is negative. Okay, the first number, it's not negative. It represents the sign negative. Why? This is 1. Okay, this is 1. 1 means negative. So this one we have to convert to, first of all, ones complement. So it will be 0 1 0 1 0 0 1 0, and you will add 1 to this, and finally you will find the decimal equivalent of this two's complement number. And we know this is actually 83 to the base 10. So this will be equals to negative 83 to the base 10. Okay, so that's how you have to do this. Okay, so this is why I wanted you to see the last video, why we are going to focus on this number. Let's say we have 1 0 0 0 0 0 0 0. Okay, remember this number? I said this is negative 128. Remember, this is negative 128 in two's complement form. Well, you can verify this by converting it back to the original form. That's it. So what we can do is, well, here we can clearly see this one is a negative number. Why? The first bit, the most significant bit, is actually a negative, the 1. So it represents a negative number. So you have to find the ones complement. So ones complement will be 0, 1, 1, 1, 1, 1, 1, 1. And if you add 1 to this, you will get again 1, 0, 0, 0, 0, 0, 0, 0. And we know this is equals to 128, positive 128. Why is it positive 128? Well, we know that you can't represent 128 in 8-bit representation of 2's complement form. Okay, so here this acts like a pseudo step. Okay, this is a pseudo number. It really doesn't exist. It's a temporary number. Okay, since this represents positive 128, that means this represents negative 128 to the base 10 in 2's complement form. Okay, so this is all you have to know in converting from 2's complement to decimal number. Now we are entering the part 2 of this video where we are going to do addition and subtraction by using the 2's complement 8-bit system. Okay, it's directly, actually it's really straightforward. Okay, it's not like a big thing or not like that. It's really straightforward. First of all, let's focus on addition. Okay, let's focus on addition. So what does addition do? Well, let's say we have 47 to the base 10 plus 63 to the base 10. Okay, so if you see this directly, you know this is equals to 110 to the base 10. Okay, but if it is that if it is really easy, why would we learn that? Yeah, so what we are going to do is we are going to learn how computers tackle this question. Okay, how computers tackle this question. So first of all, 47 to the base 10 is converted to the 2's complement form. Okay, 47 is converted to 2's complement form. Okay, so wait, 47 to the base 10. So 47 to the base 10 is actually a positive number. Okay, 47 to the base 10 is actually a positive number. So we don't have to think about converting into negative or something like that. Okay, we don't have to worry about that. So 47 to the base 10 will be 0. Since it's a positive number, first of all, we have to add 0. Then we have 47. Yeah. So how can we write down 47? Well, it will be 0, 1, 0, 1, 1, 1, 1. Okay, so this is the 2's complement form. Okay, now 63 to the base 10. 63 to the base 10 will be equals to 0. Okay, and then 0, 1, 1, 1, 1, 1, 1. Why is it 0? Because it's a positive number. Then this digit, this number represents 63 to the base 10. So if you add these two, you will find the resultant. So if you add these two, what will you get? 1 plus 1 is equals to 1, 0. So you have to bring 1 here. 1 plus 1 plus 1 is 3. So you have to put 1 here and 1 here. 1 plus 1 plus 1 is again 3. So you have to bring 1 here. Again 3. You have to bring 1 here. 1 plus 1 is 1, 0. So you have to bring 1 here. 1 plus 1 plus 1 is equals to 3. So you have to bring a 1 here. And 1 plus 0, 0, 1. And here we have 0. Okay. So what is the final answer? What is the final answer? Well, the final answer is equals to 0, 1, 1, 0, 1, 1, 1, 0. So what is this number actually represents? Since this is 0, so the answer is in positive. Okay, the first bit is 0, it's in the positive. And this is 64, 96, 104, 108, 110. So 110 to the base 10. So this is how computers actually perform this. Okay, the computers or calculators that use 2's complement representation to find the addition of decimal number systems, because computers don't understand now those numbers like 4, 7, and stuff. They don't understand that. They only understand ones and zeros. So this is how computers work. Okay, I hope I made sense. Now we will focus on another example. Okay, like maybe like 60 plus 69 to the base 10. That it won't come because 129 cannot be represented in 8-bit system, so it will be 60 plus 60. So that makes sense. So 60 to the base 10 will be equals to 0, 0, 32, 48, 56, 60, no 2, no 1. Okay, and we have 67 to the base 10, which is equals to 0, 1, 0, 0, 0, 0, 1, 1. Yeah, so now if you add these two, you'll get 1, 1, 1, 1, 1, 1, 1 to the base 0. So this is equals to 127 to the base 10. So the final answer will be 127 to the base 10. Okay, so we are just adding these two. If you have any doubts, please go through this slowly. Pause it, do it by yourself. Then if you have any doubts, go through it. Okay, now we will focus on subtraction. So in subtraction, before I go to this important stuff, just know the basic arithmetic subtraction, how it works. So if you have something like a minus b, what this means is actually a plus minus b. This is what it means. Okay, a minus b is equals to a plus minus b. What do I mean by this? Well, 700 minus 300 is actually equals to 700 plus minus 300. Okay, and let's say we have 75 minus 37. Well, that will be equals to 75 plus minus 20, minus 37. Okay, so what if you have something like minus 200 plus 73? Well, you can write it down as minus 200 plus 73. Okay, so this is a basic thing that you have to keep in mind when you're doing subtraction by using two's complement. Okay, so let's focus on this. Okay, so what happens is, first of all, okay, let's do a simple question. Let's say we have 9 minus 5 to the base 10, obviously. So first of all, convert this into the format I mentioned. This is in a minus b format. You have to convert it to a plus minus b format. So it will be 9 to the base 10 plus minus 5 to the base 10. Okay, so now what you have to do is you just have to convert 9 to the base 10 to 2's complement, and then minus 5 to the base 10 to 2's complement, and then you will add those two, and voila, you will have the answer. So 9 to the base 10 is equals to what? Well, it will be equals to, since this is a positive number, first bit is 0, then we have 0, 0, 0, 1, 0, 0, 1 to the base 2, but since this is 2's complement, you don't have to mention 2. Now you have to find out minus 5. To find minus 5, we have to start from plus 5. So 5 to the base 10 is equals to 0, since it's positive. 0, 0, 0, 0, 1, 0, 1. Okay, 1, 2, 4, the 8, 16, 32, 64. Yeah. So what will we do next? Well, now we have to find the ones complement. So it will be 1, 1, 1, 1, 1, 0, 1, 0. And you have to add 1 to this. So if you add 1 to this, what will you have? 1, 1, 1, 1, 1, 0, 1, 1. So this is negative 5 to the base 10. What do we have to find? 9 plus minus 5. So we will add minus 5 to the base 10 to 9. So 1, 1, 1, 1, 1, 0, 1, 1. So what will be the answer? If you add these two, you'll get 1, 0. So here also 1, 0. So you put 1 here, 1, 1 is 1, 0. So you have to put 1 here. It happens again, it happens again, it happens again, it happens again. And finally, you will get a number like this. Okay, it becomes like this. Okay, so now tell me, what's the problem here? The answer is 1, 0, 0, 0, 0, 0, 1, 0, 0. What's the problem here? Yes, you did it correctly. This has 9 bits and two's complement form has 8 bits. What are we going to do? Yeah, what we do is we just forget this excess bit. That's it. You just forget this excess bit. Simple, right? Very simple. I know this looks like you know how can it work? Because I mean, we have to have 8 bits. Just because we have 9 bits, you're telling me to discard the another bit? Yes, that's what I'm telling you. That's exactly what I'm telling you. Just discard the extra bit, not the last bit, only the first bit. Okay, and if you discard the first bit, you will have a number, right? And that will be the answer of the given question. Okay, so this is equals to what? We have 0, 0, 0, 0, 0, 1, 0, 0. Since this, the first one is 0, it is a positive number, and the 7 bits represent the value 4 to the base 10. So the final answer will be 4 to the base 10. That's all you have to do. Okay, so if you get 9 digits in the answer, what do you have to do? You have to remove the extra bit in the front. You just remove the most significant bit here. This is the most significant bit here. You just discard that and you just find the answer by using the last 8 bits. Okay, pretty straightforward. Ilya, let's do another practice question to wind up this. Let's say we have negative 128 plus 127 to the base 10. Obviously, you know the answer, right? The answer is equals to 1 to the base 10, but we have to do it using 2's complement form. So how can you do this? Well, first of all, we'll find minus 128. And I mean, we have done this again and again, so I'll just directly write it down. Minus 128 to the base 10 will be equals to 10000000 and 127 to the base 10 will be equals to 1, so not 1, since it's a positive number, it will be 0, and then 1111111. If you add these two, what will you get? 11111111. Okay, now what do we do? Since there are no any extra bits, you don't have to discard anything. Okay, but this number, the first digit is negative. The first digit is not negative, it's 1, so it represents negative. So this is a negative number. What we have to do, we have to convert it back to decimal. How can we do that? First of all, we have to find the ones complement. So ones complement is 000000000, and you'll add 1 to this number and you will get 000000001 to the base, and we don't have to say the base. Okay, so this is equals to positive 1. So what will be this number? It will be negative 1. So the final answer will be negative 1 to the base 10. So this is equals to negative 1 to the base 10. Okay, this is all I wanted to cover in this video, but I wanted to do something important here. So let's say you have 16 bits. Okay, you have 16 bits 2's complement representation. Well, we know if it's 16 bits, the lowest number that we can represent is 2 to the power 15 negative 2 to the power 15. Yeah, negative 2 to the power 15 is the lowest number or the smallest number that we can represent in 6-bit system. If you have any doubts, please watch the last video. I have explained how we can find this. Okay, so if you have this, okay, if you want to represent this, well, the thing is, you don't have to write this down in the decimal number and then find the answer. Okay, this one in 2's complement form will look like 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. Okay, it's just a pattern. If you have 8 bits, the smallest number that you can represent is 2 to the power 7. Okay, so that will be equals to 1 0 0 0 0 0 0 0. That's it. Okay, so what am I trying to say here? Well, if they ask you to find the lowest number, okay, if they ask you to find the lowest number by giving a random number of bits, for example, let's say they are giving 32. If they ask you to find the smallest number that you can represent by using 2's complement system by using 32 bits, well, you can directly write it down as 1000 0000 0000 0000 0000 0000 0000. Okay, so see, here we have 8 bits, here we have 16 bits, here we have 32 bits. Okay, here we have 32 bits. Only the first bit is 1. Only the first bit is 1. Okay, this is a small pattern that you can see. Okay, it's a small pattern that you can see. Okay, so with this, I'm completing 2's complement. Thanks for watching the 16th video in our number system series. If you found this tutorial on 2's complement conversion and arithmetic operations helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos, check out the full playlist to master number systems and follow us on Instagram. I'll see you in the next video. Until then, keep learning and stay curious. Bye-bye.